This video is going to cover how to solve quadratic equations by graphing. So the background information that we need to remember so we can do this with quadratics will be that we have already studied how to solve linear equations using graphs earlier in the year. And there's two different ways that we'd see these types of problems. So the first way we'd see these problems is written as two separate equations, y equals this and y equals that. So what we did to solve those was we made a graph. So I have them already graphed for us here. The red one, this is y equals 2x plus 6. We can recognize the y-intercept of 6 and the rise over the run. 2 over 1 gave us that slope of 2. We recognize the blue line only has a y value, and all these points on this line have a y value of 4, so we get the horizontal line. And we were just looking for the point of intersection, and we would use that to answer the question. So one difference, if we see it here, this system of equations had two variables. And if it's written as a system of equations with two variables, that means we need to define, or in other words, give the value of both variables. So the way we'd write our answer here would be negative 1, 4, because there's an x and a y in the original problem. So we are giving the answer for x and y. Another way we could see a very similar problem would be written like this. If it's written as one equation, what we did is we ended up splitting it up anyway to make a graph of the left side and to make a graph of the right side. Forgot my 6 there. But it ended up looking the same way. So we'd get the same point to help us answer the question, but since this one only had x, we would answer the equation as x equals negative 1, because again, there was only one variable in the original equation. And again, just down here summarizing the most important thing. We made a graph of either the first equation and the second equation, or the left side and the right side, and we're using the point of intersection to answer the original question. So a quick little reminder of how to do that. Let's solve this equation using a graph. So here, we'll do this one in red. This is just a line with a slope of negative 3 and a y-intercept of 1. So we'll start at 1, go down 3 and over 1. And we'll also go the other direction, just so we have a most complete graph we can. We'll connect those dots with a straight line. We'll move on to the right side. We recognize this would just be a horizontal line. Y equals negative 2, so we'll put a horizontal line at negative 2, and we can clearly see the point of intersection right here. It has the x value of 1 and the y value of negative 2. So the original equation only had one variable in it, so we'd answer it by saying x was equal to negative 1. So we can solve this equation by graphing, but what we should notice right away is we see an x squared term, and if we see an x squared term, that it means we have a quadratic equation. So we should see a parabola of some sort, whether it be up or whether it be down. So the first way that we're going to do this is we're going to do it very similar to the way we did the last examples. We're going to graph the left side. So we're going to treat this parabola, and then we'll graph the right side. So when we're going to graph this parabola, the first thing we're going to do is we are going to try to factor it, because if we factor it, it'll help us find our x-intercepts. We know that when we're making a graph of a quadratic parabola, we want to try to find the x-intercepts or maybe the y-intercepts and the vertex. So we can definitely factor this. If we take out the common x term, we'd have x plus 2. All right, I'm just imagining dividing both of those terms by x. So I rewrote the equation, and if I wanted to find the x-intercepts, I'd set it equal to 0. So if two things were being multiplied together to be 0, either x was 0 or the x plus 2 term was equal to 0, in which case x was equal to negative 2. So I have my x-intercepts at 0, 0, and then again at negative 2, 0. And then we want to move on to find the vertex. We know the vertex can be found by averaging the x-intercepts. So we'd add them together and divide by 2, which gives us the x value of negative 1. And we can also see that's just halfway in between 0 and negative 2. We would then plug it back into the equation. So we'll plug it back into the original equation to find the y value. So if we had x squared plus 2x, if we substituted negative 1, we get 1 minus 2, which is equal to negative 1. So our vertex has an x value of negative 1, and it had a y value of negative 1. Now at this point, we would usually just draw a parabola that looks something like this. But we want to be specific about where it's going to intersect this other line here. So I'm going to hold off on drawing the shape of the graph just for a second. So I'm going to erase that parabola shape that I just created. And what we're going to do is we're going to go graph the right side really quickly. So if that's y equals 8, that's just a horizontal line where the y value is equal to 8. So now we can start to figure out what x value we'd want to plug in to find where it touches that blue line. So what we can do is we can find one point on the right side and just use symmetry to find it on the left side, or vice versa. So at this point, we're going to make a little table here to start to find where do we think this will equal 8. And I have a guess, maybe about 2, 3, or 4. So let's try 2 first. Let's try 1 first just to be safe. So if I plugged in 1 squared plus 2 times 1, well, that's just going to equal 3. So I'm going to erase my graph here a little bit. So if we plot that point, 1, 3. If we plug in 2 squared plus 2 times 2 is 4 plus 4, which equals 8. So we actually found it there. All right, so we can label this point. We plugged in 2 and we got out 8. So now we can just use symmetry to find the other point, right? If we know the axis of symmetry has the x value of -1, well, this point here was 3 away on the right. So if we go 1, 2, 3 away on the left, this point should also have the output of 8, which I'm going to go ahead and label in red again, just so we know it's a solution. But if that output has 8, if I started at -1 and I traveled 3 to the left, that would be -4. And we can check that in our table, right? If we plugged in -4 and we squared it, and then 2 times -4, that'd be 16 minus 8, which does give us 8. So we're able to make a parabola here. And we can see that the two values that make this true for x would be -4 and 2. Now, to do the same example in a different way, which might be a little bit easier for you, it does remove some of the guess and check, but causes us a little more algebra on the front end. So 2 different ways we can approach the same problem. And by this, what we're going to do, the way that this way is different, is we're going to get it equal to 0 first. So if we subtract 8 from both sides, and what I'm also going to comment on right here, when we do that, we remember from factoring and stuff that we always want to keep a positive number. So I wrote it as being bigger than 0, but we want to keep a positive, or in other words, the leading coefficient. We want that to be a positive number. So that's why I subtracted 8. So if it's equal to 0, now what we can do is we can factor it. Technically, we do see this as another equation as y equals 0. But y equals 0, that's just the x-axis. So we're really trying to find the x-intercepts. And we know that we do that by factoring. So here, since our a value is equal to +1, we can ask ourselves what numbers would multiply to -8 and then add to +2. And for that, we can use +4 and -2. So if those two factors were multiplied and they had a product of 0, one of those factors would need to equal 0. So we'd use our 0 product property and see that the x values were -4 or the x values were equal to 2. So if I plotted this at the x-intercept of -4 and the other x-intercept of 2, 0, I can go ahead and quickly find my vertex just so we can complete the parabola, but I would add those together and I would divide by 2, which gives me -2 over 2. So the x value of my vertex is equal to -1. So then finding the output of that, if we plug it into the original equation, -1 squared plus 2 times -1 minus 8, that gives us 1 minus 2 minus 8, which is -9. So at -1, -9 is the vertex. And I'm really just graphing that so we can see that it does indeed make a parabola. And where are its x-intercepts? Well, the x values that answer the equation would be -4 and 2. Same way we got last time, but just in a different method. So another quick example that we could see when we are graphing or solving quadratics using graphs, again, I can solve this pretty quickly here. When I look at this side here, we want to recognize that this is vertex form. When it comes to vertex form, we want to try to graph that first so we can at least plot the vertex, and then maybe we can use a table or some other points to find where it's equal to 3. But I can see that this has moved to the right 1 unit and then moved up 3 units. So the vertex is at 1, 3. And then I know it would look something like that. Maybe I need to be a little more specific. But if I look at the right side of the equation, I want to know when that's equal to 3. Well, that's pretty straightforward from there. We can see that the vertex, -1, 3, is where the equation is equal to 3. So since this only has x, the answer would be x equals -1. So when we approach example number 3, something that'd be very similar to what you work on in class, we have to decide which way we want to do it. And option number 1 would just be graphing the left side on its own, and then graphing the right side on its own. So we could try that out, or what we can also try to do is get it equal to 0 by adding 16 to both sides, and use method number 2. Either way doesn't matter. I encourage you to maybe pause and try a method on your own. I'm going to go through both of them fairly quickly in this example, but just so we can see both. So if we're going to graph using option number 1, I'm actually going to graph this first, y equals -16, which means I'm going to have to scale my axes by 2. So here would be -16 if I scale by 2. I'm going to label it to indicate that to my reader that I've counted by 2 and not 1. And when it comes to the left side, again, we have x squared minus 8x. We're going to try to find out maybe the x-intercepts of that first. So we set it equal to 0, and we would use factoring. So therefore, x could have been equal to 0, or the other factor, x minus 8, could have been equal to 0. So our two x-intercepts are at 0 and 8. So 0. And then since we are scaling our axes by 2, I want to be consistent about that. So 2, 4, 6, 8. And like I said, we'll label that for our reader so they know that we're counting by 2. So what I would guess here is it's going to have to be somewhere in between there. I don't know exactly, but I'm going to check the middle first. But again, at this point now, we just have to make an XY table and start filling in some points and see where we'd get our output of -16. So we know maybe we could guess this output there, which I've put an x on, or sorry, input. And that x value, since we're counting by 2s, is actually x equals 2. So let's plug that in real quick. If we get 2 squared minus 8 times 2, well, that's equal to 4 minus 16, which is -12. 2, 4, 6, 8, 10, 12. So I'm probably going to guess 4 then. If I plug in 4 squared minus 8 times 4, that's 16 minus 32, which is equal to -16. And what we notice there is that is directly on the axis of symmetry. So that's going to be the only solution because that will be the vertex. And again, we can verify that if we were to plug in our x-intercepts and find their average, the x value of the vertex is equal to 4 there. And we know the vertex doesn't have any partner points, so this only has one solution at x equals 4. And then I can go ahead and fill in the rest of the parabola if I wanted to, but I have successfully answered the question. And very quickly, if I wanted to try like method number 2, I would have gotten that equal to 0 by adding 16 to both sides. And then from there, we would have needed to factor it. And what we could see here is that would have factored into x minus 4 times x minus 4. And what we should more commonly write that as x minus 4 squared is equal to 0, because then we can see we have vertex form. So if I plotted this, it moved right 4 and up and down 0. So 1, 2, 3, 4. Sorry, we'll count by 2s on the same graph. So 2, 4. And then that vertex answers the original question. If the vertex is at 4, 0, and I ask myself, when is the output equal to 0? Well, that would be at 4. So again, we'd only get one answer. Now the graphs look a little bit different. We're trying to solve an equation and find the x value, and we see that we get the same answer. So in this example, I'm just going to go through it one way, and what I'm actually going to do is I'm going to do method number 1, which is just graph the left side. That looks like a pretty easy parabola, and then also graph the right side, which just looks like a line, right? It looks like slope-intercept form. Looks like y equals mx plus b. So I'm going to graph the blue side first. So our slope here is 4. And our y-intercept, or our b value, is equal to 8. So 1, 2, 3, 4, 5, 6, 7, 8. I can't go up 4, so I'm going to go down 4, and left 1. So I'm going to put as many of those as I can. And then we'll draw that line in as best as we can. Now the right side is just a parabola that looks flipped over, and we recognize this from earlier. This is in the form of y is equal to ax. And we know when we did those in chapter 8 of our textbook, we were able to predict the shape, right? Since this was a negative, it was flipped over. But then the way that we graphed those was just by making a table. And we remember that the vertex on these, since it wasn't moved anywhere, left or right or up or down, the vertex has an x value of 0. If we plugged in 0, we'd obviously get 0. And then it was a good idea to try 2 or 3 x values on either side of the vertex. So if we plugged in -2, we'd be taking the opposite of -2 squared, which would be the opposite of 4, which is -4. So at -2, 1, 2, 3, 4. If we plugged in -1, and we are into the original equation, the opposite of -1 squared is the opposite of 1, which is again -1. 0 is 0, and we can use symmetry then. This point will also evaluate to -1. This will evaluate to -4. And we're not really seeing the point of intersection, so I'm going to try -3. I'm just going to have to add it down here. But if I plugged in -3, the opposite of -3 squared would be the opposite of 9, which is just -9. And that's way down here. And what I can see here is if I follow the pattern each way, this is going to keep going down like this. And this one is going to keep going down like this. And they will never touch if we continued the pattern there. And that might happen sometimes. They will never touch, which means what x values where these two touch each other, there is no solution because they never intersect. So in summary, we looked at a lot of different methods, right? So I'm going to write a few things on the bottom here. So method number 1 was graph the left side, then we graph the right side, and then we looked for the points of intersection. Sorry, I should say find. Method number 2, which we didn't do on every example, but you might be able to on most examples there. Method number 2 would be get it equal to 0 first, and then graph the parabola. If it's equal to 0, all we're really looking for is to find the x-intercepts. And the last thing that we wanted to summarize through the examples, which sometimes we did in method number 1, sometimes we did in method number 2, there was 3 types of answers that we could get, which should look similar to how we did it with square roots. But here, in our first few examples, we had 2 points of intersection. So we could have 2 real solutions. And the word real is a type of number. We saw that at one point where you graphed in vertex form that the vertex was the answer. So this has 1 real solution because there's only 1 point of intersection. And as we saw in the last example, and here I made a computer-generated graph of it so you can make sure that kind of the way that I drew it was perfect and that you knew that the pattern that they would never ever touch and I didn't have any bad lines or anything like that. So that is a computer generated version of that same example. So here there was no real solutions because they never touched. And again, when we're doing it graphically, solutions were points of intersection. So we can summarize that by 2 points of intersection, 1 point of intersection, or no points of intersection. And that's what we have.